Earth date 14th May 2021. Well, last time around, there was some sort of a misexplanation. So I had misunderstood this whole, like the converse of this proof, where you prove that it is sufficient to express any vector as in terms of the local coordinate basis or local coordinate system, right? So basically, the so once you have once you prove that like your differential curve can be expressed in the coordinate system, in the local coordinate system by this, okay, until this part it was fine. But then after this, this whole thing is actually quite trivial. So I wasn't able to quite place it. I thought it meant something a little bit more. But essentially, it means that if you have some vector as the linear combination, and you have suppose there is some, you imagine some non-linearity, and you say that, hey, essentially, because if you impose a condition of linear independence, then like any like extra or like any term that is not explainable by the current basis just vanishes. So you can just always represent your vector as in the basis of the local coordinate system. That's basically it. I mean, it's quite a trivial proof, I would say. Okay, so now let's. So today's video is actually going to focus more on a few properties of the bracket. Okay, so you'll see which bracket comes into play. So it is a precursor for the next discussion that is going to be on n forms. Right. So, and there is a slight modification that I wish to make to this scheduling of videos. So, unfortunately, when I try to make it an everyday affair, the kind of the content becomes like extremely small, and like it kind of lacks context without the before and the after, right? So in order to make a more detailed video, it'll be so I've decided that I'll be making longer videos, but like once every 2 days or 3 days. So it's going to be something around 30 to 50 minutes, but today's is going to be relatively short to brace for the weekend, and then we will come back on Monday. All right. So yeah, today's concept is basically, if you have a space of all, if you define curly x of m as the space of all differentiable vector fields on m, where like as you already saw, right, x, which is basically written by this. Okay, x can be given as some vector in this form, summation of chi j and some derivative, where chi is some constant or something, right? Given this sort of given this space, curly x and y are two vectors that belong to this space. Okay, now we define the bracket as the bracket of x comma y into f or times f is the bracket like is x, and then you take y f. So y is what are basically it's a differential, if it's a differentiation, right? So y is like you have some derivative, or you have some vector. Basically you take the vector and then you take a function. That means you get the differentiation of a function in that particular direction or that particular manner, according to how the differentiation actually works too. So once you have this, so once you have the vector, once you have the function differentiated in the manner you desire by like however the vector like wants you to differentiate the function. Okay, so you have x, you have the bracket defined this way, right? So x of, you take y and differentiate, like you take y and make it act on f. So y is, instead of a vector, it can also be called as an operator, but it's an operator in, like, it has a basis. All right, so it has like certain n components, n orthogonal or independent components, and it also has yeah, so it's and each component has kind of like a coefficient attached to it. You don't really have higher order derivatives at this particular point, but we will get to that soon, right? Once we define like the first derivative or the first partial derivative with respect to the coordinate system, I mean the local coordinates, then we can play around with it. Like that's what forms are all about. So we will get that in probably the next thing. So this is a primer, right? So first, this is how the bracket is defined. Okay, you take y, you act it on f, and then this whole thing is actually another function, right? It's a differential, like it's a function, it's a derivative of f. So a derivative of a function is another function, especially if f is of class C infinity, that is, it is infinitely differentiable. That means that this also is the function, or it is, yeah. So you act x on the function again. So you take the differentiation of f of yf with this function with respect to x now. So yeah, with respect to however x wants you to differentiate it. Okay, and understand, note this, note that x and y are essentially subspaces of the same vector space. So they may be orthogonal, they may be non, like they may have some kind of mutual overlap. So yeah, based on that, you see that this negative, this subtraction. So you take x of yf minus y of xf. All right. Because of this, like the non overlapping of x and y, there is some sort of differentiation. I mean, there is some sort of a difference between these two terms. Okay, this linear, this can be also interpreted as some sort of matrix, matrices, or like non-commutativity of matrices. So and this is what it essentially means to have the bracket, right? So now the most important thing to realize is x comma y is the vector field. What does it mean, right? If you I mean, so it's also, so you can basically write x and y, x comma y, the bracket, in the same basis that you chose to write x or y. So this, the local local coordinate essentially can be used to describe this bracket as well, is what I mean. How do you do that? Is the proof is very simple. You take x is equal to summation of chi, the coefficient, times the derivative and coordinates, I mean, and yeah, and dimension, and y is nu times the, or eta, yeah, I think it's eta, yeah. So you have chi here, you have eta, so eta times the derivative. So then you have x comma y of f is basically given by this whole thing. This is kind of like you want to probably take it as an exercise. When you actually do this kind of multiplication, you get this thing, right? This is basically decomposed into two things. One is you have this whole you have the scale, the scaling of the derivative in the first place, that is given by this whole term, that is, it directly acts on this derivative, right? So this is your initial derivative with respect to x or y, or with respect to the local coordinates. Okay, of the this is the derivative with respect to the local coordinates. Now you can also write it as I mean, you have a scaling factor because of your actions of x and y. Now to add to the scaling factor, there is also some sort of a mixing or a rotation factor, which is given by this whole subtraction thing. So basically you take to get this more clear. Okay, so you can represent this bracket in components of the local neighborhood as summation k. Okay, chi k derivative of eta j with respect to uk minus eta k derivative of chi j with respect to uk. So this indicates that there is some sort of look in the end. If you have to understand this like more intuitively, apart from the kind of like the rigorous algebra or the rigorous proof for this, so you can see here how x comma y is a different, like x is a derivative, or like x is a kind of derivative operator. A vector is an operator like that differentiates it, like partial differentiates it accordingly, as I have repeatedly told. So you have a vector, x is a vector, and f is a function. So a vector times a function gives you another function, or gives you the derivative, some sort of a derivative of the function. So now if you see the expansion of x comma y with f, okay, you see that there is well, this is going to be some sort of constant, because if you assume chi and eta to be constants and not a function, or not functions of x, okay, or not functions of so yeah, so you get this actually, yeah, I mean you get this as a linear function of u, so you don't have any additional complication. So you get this as some sort of like, so eta chi belong to the same space, right? So okay, just forget that. Now you see that there is this, if you look at f, right, you are ultimately differentiating f, taking the partial derivative of f with respect to u, that is the local neighborhood coordinates, times some particular coefficient. Okay, so that means that in the end you have something of the same dimensions or the same type as you have x f, x of f, right? So this is what I told when you have this, right? You have a differentiation of a function in some manner, right? So basically that's what it means. So so when you look at this expression as well, you see it as the components being given by so if you look at x itself, it is just the derivative, right? So you see here, as you see some sort of derivatives coming up here. So it is basically of the same comparable kind of order or magnitude, or whatever. It is of the same type essentially. Alright, now one important thing that you need to notice here is the Jacobi identity with when it comes to these brackets. So the Jacobi's identity is basically, if you take two commutators, a commutator within a commutator, okay, you need exactly three elements to kind of make it like sum to zero, okay, or it is kind of a closure property. Okay, so so this is actually quite interesting with respect to how I mean the algebra is pretty simple, right? Like if you take what the commutator bracket, I mean what the brackets actually mean, it is this, if you expand this particular x comma y comma z, so you have xy, is taking this first expansion, you have xy minus yx. Okay, now you have you take that with respect to z, so you have xyz minus yxz minus zxy plus zyx. So that's basically your commutator. I mean your that's basically the expansion of this. So if you take this expansion plus all this, the cyclic if you take the cyclic permutations of there and you do all these expansions, you see that the negative terms are exactly equal to the positive terms, so they all cancel out and become zero. This has interesting geometric implications, which needs a separate video probably in itself at some advanced level. So once you come back to we will probably come back and touch this later. So now if you have curly x of m, okay, it can be called as a module over the algebra f of m. Now what is the algebra? Algebra is basically your space of functions, right? And how the functions are correlated with respect to each other. So you have so if you have like two functions, okay, so if you have, okay, so now if you have fx, okay, which is basically your function times the derivative, so you still have uh, the operator, the vector, okay, multiplied by some function. So you are not taking the differentiation of this function, but you are rather kind of giving this function to the vector itself, okay. So that is defined, this is a fx is a vector field, right? So it belongs to the category of a vector field because you are taking fx, right? You're not taking the derivative of f, but you are rather giving the differentiation or the vector some function property, right? So this is given by so fx of at the point p on a manifold. So you have f of p times the coordinates or the chi, the summation chi dou by dou u j rp, okay. So this is what it essentially means. Now if you have two functions, so this is where my earlier thing about algebra is coming from. So if you have two functions f and g, then the algebra is basically it tells you how as you move from x to y, or as you move uh, if you take a particular tangent space, okay, and then you have a vector there, so you can kind of transition the vector in a particular way, and you can transition it in like different ways, right? Okay, so how are all the ways related to each other, how they flow into each other, is something that is given by this by this algebra, that is f curly f of m, right? So you have now to define the brackets. Okay, this is actually rather somewhat trivial. Okay, so you have the bracket of fx comma gy. You do this, you apply the product rule on function with the bracket action, that is the commutation, like the negative x y minus yx, you take that, okay, you get this kind of relation, right? So now basically your f comma g belong to the module, that is, it kind of gives you a structure as to how f and g are related to each other, and the manifold gives you like how x and y are like kind of positioned on the tangent space, right? I mean, so right, so this is something that is probably interesting because it gives you I mean, it tells you how it tells you two things, right? Earlier or so far we have been talking about either the vectors or the functions themselves. Now you talk about this combined action of both vectors and functions, which is what gives the manifolds somewhat very rich structure and like rich correlation with respect to like what the what each like how each point is correlated on the manifold, right? So basically, like once you understand this, Okay, once you understand up till here how what exactly is the meaning of a function and what exactly is the meaning of a vector, and how the brackets really work. Okay, so the brackets come into use. They essentially give you some sort of difference, as I told, between how one can be described in how each vector can be described in a particular neighborhood, right? So not every vector can be like described in the same way in the same neighborhood or in the same local coordinates. So you need so the difference between the two gives you some sort of a structure that is correlated to, you know, the curl or the gradient or the shape of the manifold itself, right? This is something that is an observation for now, but as we see later, you have interesting properties arising from this particular difference. It is just like how yeah, so we'll hold on for that on that thought for a bit. um, so now coming to the definition of one form, right? Like the derivative of a function, the total differential, like you have this particular vector or the operator on the function, the total differential is something that is dual to the tangent space of the derivative. So if you have this, I mean, tangent space of the manifold, not of the derivative, sorry. Tangent space of you have yeah. So this is something that is dual to the tangent space of M. So what do you mean by dual to the tangent space of M is quite interesting. All right. So now the differential, is given, the total differential is given by summation of f with respect to du times the coordinate, the differential of the differential element of the coordinate. So the differential element gives you a dual of the vectors. Okay, so if if df belongs to the dual of the tangent space and x belongs to the tangent space itself, then you have the angle bracket. So this is rather the this is something that we will see soon, right? So if you have the angle brackets, which basically takes this is um, so so we have the angle brackets on of the differential on the vector, so which is given by the derivative of the function itself. So you have the differential on the vector in angle brackets, which is basically the differential of the vector itself. The differentiation of the function itself in that particular neighborhood. Alright, so yeah, so this is something that is a representation rather. Okay, so and it helps to understand how df actually makes some kind of intuitive sense here. Alright, so now a couple of things to think about over the weekend until we have our next we resume our discussion. Okay, so this is for a differential to be of some value. So ultimately at the end of the day, you are not looking to just kind of, you know, talk about how functions or everything just changes, but you're also looking at describing how you're trying to extract some information, and that information comes only in the real in some as a form, in the form of some value, right? So for a differential you need to integrate it. So if you have if you have some f of x comma y comma z, and then you have the total differential as f of dx plus f dy plus dz, where f is a function of x, y, z. So you need to take the integration of this, right? Okay, so this is one stream of thought. The second stream of thought is for the missing element of a tangent vector. So what do you mean by this particular vector, tangent vector in some neighborhood? Okay, so what do you need to complete this and extract some information out of this? You need a function, right? So when and you see these two, the differential and the tangent vector, are duals of each other, and duals necessarily mean some sort of either inversion, or they talk about like, if you are giving some sort of a as we saw earlier, right? If you have a vector, the dual space of the vector is like how your functions are forcing the vectors to change, right? So or like how the functions are acting upon your vector. So when you take those two things, you see, like, you try to understand what it really means to have a manifold with a differentiable structure, and yeah, how it is all not very trivial, right? So you have you have something that is quite interesting going on here. And so with this thought, we pause for today. As I said, right, the scheme of things is going to change a little bit because I want to cover things to a better completion in a single video, so that there is no so that it doesn't become very point size it doesn't become a point size exercise each time as I go through something, right? So there is some expansion, there is some kind of elaboration on the right topics. So with that in mind, we will have we'll have it more spread out over the next few weeks or months. So yeah, see you for now. Hope to see you on Monday. Bye bye.